Hello. So in this example, we have this rather large word problem, right? And this is going to be a optimization problem. So looking at the problem, right, we have a farmer wants to enclose a rectangular field. One of the sides of this sort of fenced-in area is like a river or some natural boundary, so you don't have to use fencing. But then the rest of the sort of fence together, he has 500 feet of fencing to allocate. He wants to enclose the most area. So we want to figure out what the dimensions are that makes that happen. So first step of really any word problem in general, but especially with like optimization problems, we want to draw a picture and use this as sort of a reference tool. So we have this sort of rectangular fenced-in area. Now it has some, let's say, length and some width, which we don't know. And, right, we don't have to be artists here, but one of the sides is sort of enclosed by the river, right? So really the part that has fencing is just on these side pieces on the left and right, and the one width part over here, okay? So now we want to sort of use what we've written here to model what's being told to us. So in particular, we know two pieces of information. He wants to enclose as much area as possible, and he has this sort of limited amount of total fencing. In particular, he has 500 feet of fencing, all right? So you have 500 feet of fencing to spend going along these three edges, which I've labeled L and W. And because it's a rectangle, we know this one over here is also an L, right? So in particular, then we have 500 feet of fencing, and assuming he uses it all, this is going to be 2L plus W, right? And of course, if he's trying to get the biggest area he's going to use all of it, because otherwise, he could have made it bigger and gotten more. So this is our constraint, right? This is the thing that's sort of stopping us from going crazy and just enclosing, the world in our fence, right? So we only have so much fencing. But the thing that we want to achieve is the area. We want to maximize the area. So the area for what we've drawn here, right, this area inside, well, it's going to just be length times width, right? So length times width, this is going to be our sort of primary function, or the thing that we're trying to optimize, right? We want to, in particular, maximize this. Okay. So we've drawn a picture. We've written out the sort of relevant equations that we know. One is the constraint. That's the thing that's sort of holding us back. But really, before we thought of it as the constraint, we were like, okay, what do we know? We know he has 500 feet of fencing. So we know that length, and that length, 2L plus W, has to be 500. Then we also know that, or we are sort of, our goal, right, the whole hope of this process is to maximize the area. So again, using our picture, we had to come up with something that represents area. But rectangles are nice, so our area is just length times width, and that's area, which I guess, to be very clear, I'm going to call that A, right? That's what I wrote here. So our goal then is to maximize A, find the largest possible A. Okay, well, if we had A as just one variable, right, if A was just some function of L or some function of W alone, didn't have both of those, I could use like a derivative and find a local max or a global max, right? But unfortunately, I have two variables, so I don't really know how to deal with two variables, at least not yet. But I do have this other equation. So what I'm going to do is use the constraint equation to sort of drop down the number of variables to one variable, so that then I can use my calculus, right? So I could solve for L or W. Either one would be fine. W is sort of a little easier, I guess, because I wouldn't have to divide anything, so I'm just going to move the 2L over. So I'm going to move the 2L over, and that gets me that W is 500 minus 2L. And this sort of makes sense, right? Because however much of the 500 fencing I have, if I take away the parts that I use on these two edges, that's exactly what's left over, right? So this geometrically makes perfect sense. But I can substitute in then what W is into my area equation. So my area, which is normally length times width, I can write as length times, and then sub in what width is, 500 minus 2L. And then distributing my L, I'm going to get 500L minus 2L squared. But now my area is indeed in terms of one variable. So now I can look at the derivative of area with respect to L, right? Because what I'm really asking is, what is the maximum A, right? And so if I'm looking for the maximum of a function, then I can use my first derivative to find extrema, right? So if I look at A prime, I'm going to get, right, this is 500. I technically have a 1 there, so bring the 1 down, subtract 1, but that's just going to get me 500. And then bring down the 2, I'm going to get 4 times L to the 1. And so I'm looking for when the derivative changes signs. In particular, as usual, that means I could use a sign chart. I'm looking for these critical points, right? So if I factor out a 4, I'm going to get 4 times 125 minus L, which means that this is going to be 0 when L is 125. And if I look at my sign chart for 125, if I pick some really large number, I'm going to have subtracting a much larger number, so that's going to be negative. And if I look at some really small number like 0, I'm going to get all positives. So that's up, that's down. That tells me that when L is 125, I do actually hit a maximum. So A has a maximum at L equals 125. Now, it's important to note that I'm not done, right? My goal is to determine the dimensions of the field that encloses the largest area. Well, I have one of those, but I need both, right? So I need to know what W is, but at some point I solved for W to sub out what it was, so I can use that equation with my new L to figure out what W is, right? So I know W is 500 minus 2L, which is 500 minus 2 times 125, which is 500, 500 minus 2 times 125 is 250, so that is 250. So then, the answer to my question, right, my dimensions, are 125 by 250, where these are both in feet, right? Because my original thing was 500 feet. And I'll make a note here where the river is opposite the 250-foot side of fence. Right, so to be clear, right, the W was 250, right, that's what we solved, was this was 250, this is 125, and so the river is taking up the other side of the 250, right? So this is my answer, okay? So picture, develop the math language, right? The primary function, the thing I'm trying to max or min, trying to maximize. My constraint, use the constraint to get rid of one of the variables in my optimizing, right, my primary function. Then find the optimal value, in this case the maximum, and then I can calculate what I need to calculate, okay? So that's that. Hello, so in this example, we are doing another glorious word problem. So this one is optimization problem. So you work at a company, right? Company wants to redesign their product packaging into like a normal box shape. This particular box is going to have a square base, and the bottom needs to be reinforced. So we want 2 layers in the bottom. Now, we know from pricing of materials and stuff, we have these 200 square inches of cardboard to be used for the box, and we want to know sort of what the dimensions are that will sort of maximize the usage of this box. Okay, so where to start? Well, as sort of is always the case, we want to start with a word with a sort of visual representation of our word problem, right? So we can start by drawing our box, which, you know, don't judge, I'm not an artist. So we have our box here. So go sort of three-dimensional box style here. And sort of have the back as well for the box. And I'm gonna go ahead and label some dimensions here. So we have the height, h, we have the, let's say width, w, and the length for that sort of going up and back part. Now, we have some goal, right? So our goal is to have the dimensions that encloses the largest volume, right? So we want to write an equation that sort of represents what we're trying to optimize. So in this case, we want volume, right? So remember volume for a standard box, right? So volume is going to be width times length times height. And remember that this thing has a square base, which tells me, even though I wrote, right, width, length, and height, that this bottom is a perfect square, as would be the top, right? But that tells me really that width is the same as length. Width and length are the same value, so because that's how we make a square, right? And we want to sort of make the biggest volume we can, but the constraint, the sort of limiting factor, the reason we can't make a box the size of the universe or something, is that we only have so much material that we can use, right? So we need to sort of interpret the amount of material into an equation. And sort of the way to think about that is we have this sort of box that's made of this cardboard. So the material is really all of the edges, right? Which really translates in a math sense to the surface area. So we need to calculate the surface area because that's really how much the material is getting sort of used, right? So in general, our surface area is sort of each of these panels is mirrored. So for example, length times height would give me the area of this side piece, but that is mirrored on the other side. So I'm going to have 2 times for each of these. So 2 times. So I have 1 length height, 1 length height. So I have 2 length height. Then I have 1 length width, 1 length width. So I have 2 length width. And I have, let's see, the front and the back panel, which are height and width. So I have 2 height and width. So this would be if I just did the standard surface area, but remember, the bottom needs to be reinforced. So I need an extra, whatever the bottom is, which is width and length. So really this would be 3 length width, but I'm just sort of doing it as I sort of see it, right? Okay, so I know that the amount of material then, because that was my constraint, right? 200 square inches for material is my surface area. So I know that my surface area limit is 200. So all I've done so far is just sort of record the information I have. Now I'm going to go about cleaning it up a bunch. In particular, I know that width is length, right? That these things are the same. So I'm just going to basically go through all of my formulas and change my L's into W's, right? Because they're the same, so I can reduce one variable right away. And then I'm going to clean up the result, because there's probably going to be a bunch of similar terms as a result in the surface area equation at least. For volume though, right, I can replace my length with my width here too, which will get me width times width, or width squared times height. And for surface area, I'm still going to have 200. But here, I'm going to have, let's see, 2 times width times height 2 times width squared, right, because that's width and width, plus 2 times height times width, plus width times width, so width squared. And now I can put this stuff together. So I have width, height, so I have 4 times width times height. And then I have 2 and another one, so I have 3 width squared, yep. Okay. So now, these are my 2 equations. Now my goal is to optimize the volume, right? But again, if I had sort of just one variable, one unknown, I could use my calculus to find the maximum or minimum, in this case the maximum of the volume. But I have more than one variable, so I can't quite do that. Instead, what I'm going to do is use this equation down here to solve for one of the variables and then substitute that out in order to get rid of that and put it in terms of the other one. So I'm going to take this equation down here, and I could go either way. I could isolate width or height, but looking at this, it would be much easier to isolate height, so I'm going to do that. So I'm going to start with, let's say, 200 equals 4 times width times height plus 3 width squared. Okay. So I want to isolate height, so I'm going to move my width part over. So I have 200 minus 3 width squared equals 4 width height, and then divide both sides by 4 width, 4w. So I'm going to have 200 minus 3w squared over 4w equals h. Then I could take this h and plug it in as that h, right? So my volume then is going to be width squared times height. So 200 minus 3w squared over 4w. Now, it's a little dodgy to divide by 4w because w is a variable, and I always have to worry about dividing by 0. But remember, w represents the width. So the only way 4w would be 0 is if the width was 0. And that's not really a box anymore, right? Like, if my width is 0, I'm now down to a slice of cardboard. That's really not going to hold a lot. So it's sort of worth a note mathematically that I've sort of eliminated w equals 0 as a potential answer. But sort of according to the actual model, right, the actual thing I'm modeling, that is sort of no problem. I don't have to worry about that. Okay. So then one of these w's can cancel that w, so I'm going to end up with 200w over 4 minus 3w cubed, right? Because one of these cancels that, so then I get w times 200 over 4, and there we go. It's like I thought I was missing something. And then w times this, so I get minus 3 over 4 w cubed, which I can clean up a little more. I can make that 50w minus 3/4 w cubed. Okay, so far so good. So now I have my volume in terms of one variable, which is good news. So now I want to find the maximum that I can attain, right? So in order to find the maximum of this, or more particularly where the maximum would occur, I'm going to take my derivative, right? So taking my derivative, v prime. So here I get 50 minus, bring the 3 down, so I'm going to get 9/4 w squared. So I can interpret this as a difference of squares, as weird as that is, because I can think of this thing as being something squared and this thing as being something squared. So in particular, I guess if I actually did out the square, this would be 5√2 squared. So that's just taking the square root of 50. And this would be 3/2 w quantity squared, again taking the square root of 9/4 w squared. And I do that because this gives me 3/2, well, I'm doing this by sort of on autopilot, I'm putting the variable first, but that might confuse, so I'm gonna not do that. So I'm gonna have 5 root 2, so this is like a squared minus b squared, so I get a minus b times a plus b. Okay. So this means that I have zeros where either of these are 0. So they're going to be 0 sort of in the same spot, but with different signs. But regardless, I can sort of set one, I can set these equal to 0 and solve, which maybe I will do off to the side just because they're super weird numbers. So I would have something like 5 root 2 minus 3 halves w equals 0. So then I'd have 5 root 2 equals 3 halves w. That's just moving the w part over. And then multiply both sides by 2/3. So I'd have 10/3 root 2 equals w. So this tells me that the solution for when this equals 0 is going to be 10/3 root 2 for w. And this one is going to be the same, but the sign is going to be flipped. So it's going to be negative 10/3 root 2. But sort of importantly, right, this thing, again, is a real system. So just for the same reason that like I wasn't too worried about missing out on the w being 0 solution, there's no way that I'd have a negative width, right? So this one doesn't even make sense to really consider. So I really want to look at then the sign chart, where I'm going to look at 10/3 root 2 and 0. I'm choosing 0 not because it is a 0, but because it's a limit of our system, right? Again, w can't be 0 or less. So I need something here and here to check the sign. So I just need to know like a number that's roughly around 10/3 root 2. For example, 10/3 is more than 3, root 2 is more than 1. So if I pick something like 2, which is less than either of those, I'm definitely going to have something in this range. So if I plug in 2, say here, and see what I get 50 minus 9/4 times 2 squared, which would be 50 minus 9 is positive. And I could pick some ginormous number way off to the side, like positive 1 billion, in which case 50 minus some huge number is going to be definitely negative, meaning that this thing definitely goes up, then down. So I am indeed finding the maximum, okay? Which is good news, because that's what I wanted, right? So this tells me that I have the maximum, max occurs at w equals 10/3 root 2, in our case inches, right? Because this is what the thing was in, 200 square inches. So I'm doing all of this in inches. And then I need to actually calculate what h is, right? Because w is L, so I know that I have w. Since I have w, I have L. So all I have left then is h. But I solve for h up here. So I can, let's use green again, why not? So I'm just going to sort of do this part off to the side somewhere. I want to do it there, but I want to have the answer there. Maybe I'll do it down below. So my h is 200 minus 3 times 10/3 root 2 squared over 4 times 10/3 root 2. And yeah, this isn't a nice number, but it is what it is. Like we just roll with it. So I'm going to get 200 minus. So here I'm going to have 10 squared over 3 squared, but then times 3. So one of those will cancel. So I'll have 100 over 3 times 2. So that's going to be 200/3 over. And then down here, I'm just going to get some awful number, 40 over 3 root 2. And to make that a little bit nicer looking, I'm going to multiply everything by 3 because that'll cancel out that 3 and that 3. So I'll get 600 minus 200 over 40 root 2, which is going to give me 400 over 40 root 2. And that's good news because the 400 and the 40 cancel down to a 10 on top. So this is going to get me 10 over root 2, or if you like, you can rationalize the denominator, not that you need to, which will get you 5 root 2. Because you'd have a root 2 on the top and bottom, which would get you 2 on the bottom, and that would cancel down to 5. So I know that W is 10/3 root 2, and H is 5 root 2 inches. And my L, remember, is the same as my W, so this is also 10/3 root 2. So my box dimensions would be 10/3 root 2 by 10/3 root 2 by 5 root 2, where all of these are in inches, right? There we go. All right, so as a quick recap, as with pretty much every word problem ever, draw a picture so that you can sort of see how the different information fits together. Come up with an equation that sort of represents the thing that you're trying to max or min, like the thing you're trying to optimize. And come up with an equation or formula that represents the restriction, right? The information that you had that sort of stops you from making the absurd case, right? A box the size of the universe or something like that. Then, typically, as was the case here, you use that restriction to help get the number of variables down to one variable in your optimizing function. So here we had W and H, so we had to manipulate this to get rid of H so that I had just something in terms of W, which is what I did. But then I can use calculus, right? Take the derivative of this thing and then find the max or min, right? I found the max at this value, and then use that to get all the other values. So I had W, which gave me L, and then I just had to actually calculate H. That got me HL and W, dimensions of my box. So that is that.